Today, we're going to make the invisible, well, visible. We are diving into the four fundamental forces that are running the show for every single object around you, from the phone in your hand to the planets way out in space. These are the basic rules for how things move, or stay perfectly still in our universe.
Okay, let's just jump right in with a question. Think about it for a second. Right now, what is keeping you from floating off into space? And what's keeping your chair from crashing right through the floor? The answer is a bunch of invisible forces. And by the end of this, you're going to be able to see all of them.
So, first things first, we got to get our key terms straight. In physics, a force is actually super simple. It's just a push or a pull. That's it. It's what you need to make something change its motion. You know, to get it started, to speed it up, slow it down, whatever. And we measure force in a unit called newtons.
To really get a handle on all this, we're going to stick with a really simple example. A book, just sitting on a table. And we're going to use this awesome tool that physicists use called a free body diagram. Don't worry, the name sounds way more complicated than it is. It's really just a simple sketch to help us see all the forces at play. All right, force number one is the one we all know and love, gravity. We'll label it Fg. It is the constant downward pull that the Earth has on the book, on you, on everything. And it's a long-range force, which is pretty cool, right? That's why the Earth can pull on an airplane without even touching it.
So, here on Earth's surface, that gravitational pull makes any falling object speed up at a constant rate, 9.8 meters per second every second. This number is also key to figuring out an object's weight. See, your weight isn't actually your mass, it's the force of gravity on your mass. You just multiply your mass by this number, 9.8, and boom, that's your weight.
Okay, but wait a second. This brings up a really important question. If gravity is constantly pulling the book down, why isn't it moving? I mean, shouldn't it be accelerating downwards? What is stopping it from just falling straight through the table?
The answer is our second force, the normal force, which we'll label Fn. Now, in physics, normal is just a fancy way of saying perpendicular. So the normal force is just the support force from the table pushing straight up on the book. It's the table basically saying, nope, you are not coming through me.
And this is a perfect example of Newton's third law. You've heard it, right? For every action, there's an equal and opposite reaction. Well, the action is gravity pulling the book down. The reaction is the normal force pushing the book up. And since the book isn't flying up into the air or crashing down, we know those two forces are perfectly balanced. They cancel each other right out.
Okay, so our book is sitting there perfectly balanced, but what happens if we try to, move it? Imagine you give that book a little nudge to slide it across the table. You feel that pushback, don't you? That kind of drag. What is that force that you're fighting against?
That resistance is our third force, friction. We'll call it FF. It's a force that always pushes back against motion when two surfaces are rubbing together. It's caused by all these tiny, microscopic bumps on the book and the table catching on each other. And friction is incredibly important. It's what lets your brakes work and what lets you walk without your feet slipping out from under you.
But it turns out there are actually two kinds of friction. First up is static friction. Think of this as the stickiness that you have to overcome just to get the book to start moving in the first place. Once it's actually sliding, now you're pushing against kinetic friction. That's the resistance that acts on it while it's moving.
So here's the main takeaway from that. Static friction is almost always stronger than kinetic friction. To put it simply, it takes more of a push to get something moving than it does to keep it moving. Just think about pushing a heavy piece of furniture. That first shove is always the hardest part, right?
All right, let's switch up the scene one more time. What if we get rid of the table completely, and instead, we hang the book from a string? Gravity is still pulling it down, of course, but the normal force is gone now. There's no surface for it to push off of. So, what's holding the book up?
Well, the force holding the book up this time is our fourth and final one, tension, which we'll label Ft. Tension is that pulling force that you find inside a string, or a rope, or a cable when it's pulled tight. It's the force that's at work in the cables of a giant suspension bridge, or in the line a crane uses to lift something really heavy.
So let's just make sure we're super clear on the difference here. A normal force is a push that comes from a surface and it resists being squished. Tension, on the other hand, is a pull that comes from a string and it resists being stretched. So one's a push, the other's a pull. But in our little examples, they both did the exact same job. They fought back against gravity.
And now for the grand finale. Let's put everything we've learned together into one final scenario. We're going to pull our book across the table again, but this time we're not going to push it. We're going to pull it with a string.
And there you have it. In this one simple everyday action, you can see all 4 of our invisible forces at work at the same time. You've got gravity pulling the book down, the normal force from the table pushing it up, the tension in the string is pulling it forward, and the force of friction from the table is pulling it backward, resisting that motion. It's like this constant invisible dance of pushes and pulls.
So here's a final thought for you to take away. These forces aren't just ideas in a science class. They are literally the code that runs the physical world around us. So the next time you see a car driving down the road or an elevator going up, try to picture that free body diagram in your head. Can you see the invisible forces at work? Because once you learn to see them, I promise you will never look at the world the same way again.